Hi friends, welcome back to Edupedia World. The last lecture we discussed about the different ranges of electromagnetic radiation, the different radiations there are. We saw their wavelength and the frequency ranges. Today we will continue from where we left in the last lecture, and we will discuss the sources, the properties and uses of each of those radiation, specifically of gamma rays, X-ray, ultraviolet, visible, infrared, microwave and radio waves. So let's start with our discussion on gamma rays. So we know that the electromagnetic spectrum is composed of several segments, and as we discussed, the segment which is the most energetic or which has the least wavelength is known as the gamma radiation. And gamma radiation, as we discussed, is approximately 0.1, less than 0.1 angstrom in length. Okay, now what are the sources of gamma radiation? The sources of gamma radiation mainly are the radioactive materials. So when a radioactive material decays, then it produces radiations in the range of gamma rays. And a second source is cosmic radiation, the background radioactivity of the universe. There are black holes collapsing and pulsars and a lot of very volatile activities and violent activities going in the universe, which radiates out a lot of energy and very high energy radiations. So those falls in the range of gamma radiation. Now if we see what are the properties of gamma radiation, in addition to the general properties which we discussed about all the radiations, some specific properties which are characteristic of gamma radiations are that it is a high, very high energy radiation. Why so? Because energy is H is equal to E nu, rather E is equal to H into F. Let me write it down. So E is H times frequency, where H is a constant known as Planck's constant, and given that the frequency is very high, the energy of the radiation will be very high. The frequency is speed of light upon the wavelength. So alternatively we can write the energy as hc upon lambda. H is a constant, speed of light is a constant, 3 into 10 power 8 meter per second. So smaller the wavelength, larger is the energy. Since gamma radiations are the smallest wavelength radiation, they have very high energy. They also cause fluorescence. If we have a fluorescent material and gamma ray is incident on that, we can observe fluorescence happen. Okay, now given that it is gamma radiations are very high energy radiations, it's not difficult to think that they can penetrate through thick metallic sheets, right? Since they have a lot of energy, they require a very thick layer of material to stop it from penetrating. Therefore gamma radiations have a high penetrative power, that's what we say. And also, since it is a high energy radiation, the chances that a gamma radiation, if it falls on you, will cause permanent damage, biological damage. It can cause genetic mutations in the body, DNA alterations. So it is very important not to get exposed to gamma radiations, as it can be lethal or highly damaging to the human body. Now let us see where are gamma radiations used. I just now introduced you to the idea that gamma radiations are highly biologically damaging, has high biological damaging properties, but this, if used in a controlled way, is very applicable for cancer treatment. Now, as you might be knowing that cancer is basically a mutation or changes in the body, certain tissues goes bad in the body. So if we locally target those tissues, then using gamma radiations, then it can be used to kill out those harmful tissues, and hence is used for cancer treatment. Second, gamma radiations has several industrial applications, like they can be used to detect ununiformity, or let's say some fracture or some discontinuity in industrial machines or pools or bridges, things like that. Okay, so after gamma radiation, the second in line is X-rays. X-rays are radiations which are just a little less energetic than the gamma radiations. So they have a slightly higher wavelength. These are angstrom, 0.1 angstrom to 100 angstrom normally. But this in itself is also a very high energy range. So we can say that X-rays are just a little less energetic than the gamma radiations. Now, how is X-ray produced? The most important source of X-ray that is used by scientists and experimentalists to produce X-ray is basically striking high energy electron on heavy metals. Now, what this does is this high energy electron on striking metals, they strike out the electrons to higher energy shell, and when the electron goes back to its original state, then X-rays are radiated out. You need not understand the details, but we will discuss it in a later chapter, but you should know that it can be produced in this way. Now, what are the properties of X-ray? The properties of X-ray is similar to the gamma radiation. This can also produce fluorescence. Okay, and given that it is highly energetic, similar to gamma radiation, it is very chemically active radiations. And since this is highly energetic but slightly less than the gamma radiation, these X-rays can also penetrate through thick regions like the human body. But a catch there is that the X-ray can penetrate through the human skin, the muscles and stuff, but it cannot pass through the bones. It is stored by human bone. Now, this very property of it being able to be stored by the bones of the body is put to its use in the medical purpose of fracture detection. So medically, if bone fracture takes place, then what happens if you impart the X-ray on the human body, then if there is no fracture in the bone, the whole bone can be seen because all the radiations are stopped by the bone. But if suppose there is a slight fracture in the bone, then there might be some space for the X-rays to penetrate through. As a result, we will see a dark spot in the scan. Okay, or alternatively, if the bone appears dark, then we can see a bright spot in the scan. So a medical application, it is a very day-to-day application which you see everywhere in hospitals, X-rays available. Then for spectroscopy, if you want to see the internal structure of atoms and elements, then X-rays is used to detect those things. Now, the third range of radiation is called ultraviolet radiation, lies in the range of 100 angstrom to 4000 angstrom. One very important natural source is the sun. So the sunlight which is reaching our earth has a lot of ultraviolet radiation in it. Artificial sources included electric arc in industries, where a lot of ultraviolet radiation is produced by the electric arc and spark. Now the properties specific to ultraviolet radiation is that it is scattered by dust. So the atmosphere kind of provides a sheet of protection against the ultraviolet radiation. It scatters away the ultraviolet radiation that is coming from the sun. Also, the ozone layer in the atmosphere absorbs the ultraviolet radiation, and hence it stops entering the surface of the earth. Similar to the previous to the gamma and the X radiations, the ultraviolet also causes fluorescence. Finally, the ultraviolet radiation is known to cause skin cancer. That is why it is very important that the ultraviolet radiation from the sun do not reach earth, or even if it reaches, it is in very small quantity. As a result, the presence of ozone layer is a very important safeguard against skin cancer and damage caused by ultraviolet radiation. But there is some upside to ultraviolet radiations too. One is that it is used for sterilizing purposes. It's used to kill germs and harmful bacteria, and is used extensively in the medical industry. Secondly, which directly affects us, is that it helps in ultraviolet, vitamin D production. It itself does not produce the vitamin D in the skin, human body, but it helps in vitamin D production. So an important thing to note is that though we do not want to overexpose ourselves to ultraviolet radiation from the sun, we want some exposure to the sun so that we have the minimum required intake of ultraviolet radiation from the sun to produce vitamin D in the body. Next up, we have the visible range, the range which is most common to us, and it lies up approximately 4000 angstrom to 8000 angstrom. Here is the 4000 is close to the violet region, and this is close to the red region of the visible range. Now the sources are obviously sun, the white light produced by the sun. Then every hot body, if you heat a body sufficiently high temperature, it will radiate out visible radiations. Like for example, if you heat a bar of steel to, let's say, somewhere 1000 degrees Celsius or even further, then it will become red hot, and as a result radiations in the range of red light is emitted by that body. Also flames and other things are sources of visible radiation. The property of visible radiation is that it is visible to the human eye. Obviously, that's why it is called the visible radiation. Second, it does not cause fluorescence. So this is a difference. Does not cause fluorescence. Okay, and finally, where is it used? The uses of visible radiation, very important, help us see, obviously, and second, it's in photosynthesis used by the plants. You might come up with many more uses of visible light, but I will restrict to this. Then beyond the visible light, we have the infrared radiation. The infrared radiation is in the range of 8000 angstrom to approximately 10 to the power 7 angstrom. Now, what are the sources of infrared? Infrared is produced by all hot bodies. Any body which is hot, or even the human body at its normal temperature of 37 degrees Celsius need not be hot as in 1000 degrees Celsius. Even 37 degrees Celsius human body produces infrared radiation, and this very property is used in the night cameras to take photographs because light cameras are able to detect the infrared radiation, and all human bodies emit radiation in the infrared range. Hence we can take photographs at night. We'll see that in the uses. So one of the sources human bodies or other hot bodies. Then sun is an extensive source of infrared radiations. The properties, it does not affect normal photographic plate, but if there is some specially treated photographic plate, then it is possible for the infrared to affect that, but normal photographic plate does not affect and is not affected by the infrared radiation. Now, very distinctive property of infrared radiation is that it causes a heating effect. So this is a very distinctive property of infrared radiation, heating effect. Next, as we have reached the infrared zone, we have already come to a very high wavelength zone, right? So high wavelength is associated with less scattering. So the higher the wavelength radiation you are dealing with, less will be the scattering. As a result, infrared radiation is one of them and causes very less scattering. We have seen that infrared has a heating property, which is typical to it. So if you overexpose yourself with infrared, then you can there can be skin burn. So infrared can cause skin burn. It's advised to take care not to overexpose yourself to infrared radiations. Now let us see some of the uses of infrared radiation. The remote control, the TV remote control, the AC remote control that you are using normally works in the infrared range. So that is one of the uses. Then, as I discussed, night photography is possible due to the exploiting the infrared range of the light. And there are certain therapeutic treatments that can be where infrared radiations can be used. Then next up, higher up the wavelength, we have microwave radiations, which are approximately in the range of 10 power 7 angstrom to 10 power 10 angstrom. Just to remind you, in the previous lecture I have mentioned that this can vary. Some places it says 10 power 9, some places 10 power 11, some places 10 power 10. But what I saw in general is like 10 to power 10 angstrom. In the previous lecture I had mentioned 10 power 9, so kindly rectify that. And now we have seen that we are already in the meter range. So 10 power 10 angstrom is 1 meter. So we are already in very large wavelength region. What are the sources of microwave radiations? Electronic devices produces a lot of microwave radiation. Also, one of the most natural sources of microwave radiation is the background radiation from the Big Bang. During the formation of the universe, there was a lot of background radiation produced, which is still detected, and those radiations are in the range of microwave radiation. So this is a very astronomically useful parameter or useful source, and scientists extensively use this to study the formation of universe and galaxies. Now the property, very typical property, is that it is in the very long range wavelength region and hence less energy, which results in very less scattering, Okay, so microwaves have very less scattering properties, and also it has heating properties which we exploit in the microwave oven. So this is one of the uses. Now, since this has less scattering, satellite communication uses microwave radiation because you want the whole information to get transmitted in the form of waves. You do not want to use something which gets scattered midway. Therefore, we use microwave radiation. Also, radar communication uses microwave radiation for the same reason, that it has less scattering. Okay, now ultimately we have what is called as the radio waves. As the name suggests, you can say that it is somehow related to radio and television or communication in general. Similar to the microwaves, this has a very long wavelength, and hence this is the least scattering waves. Hence the name radio waves, because it is used for communication. Now its wavelength range is greater than 10 to the power 10 angstrom or greater than 1 meter. It is produced by electronic devices for communication purposes and stuff, and also cosmic radiations. The universe produces a lot of high wavelength radiations which we receive on Earth too, and hence is a source of radio waves. We already saw the property high wavelength, least scattering, and as can be obvious from the fact that least scattering, it is going to be used in communication extensively. All the radio transmissions and the TV signals that you get on your television set, it uses radio waves to transmit the information. Okay, so I hope you have a good picture about the different parts of the electromagnetic spectrum, the different radiation ranges, and what are their some useful uses, some typical properties, and some sources. I hope this has been an exciting and informative session on electromagnetic radiations. Next, we will discuss something which is very visible day to day. Why is the sky blue, or why is the sky reddish in the evening? Things like that. That has to do with scattering too. So I will wait for you to join me in the next lecture. Till then, have a great day. Goodbye.